Hello audience, this is Yue Song from the University of Hong Kong. I'm glad to give a talk titled Energy Management in Low Voltage Power Systems, benefiting from network side flexibility, based on some recent research progress in our group. This is the outline of my talk, and let's begin with the motivation of this research. In response to the environmental concern, the low voltage counterpart of power systems, such as distribution systems and microgrids, are having increasing penetration of renewable distributed generation. However, the intermittency and the uncertainty nature of renewable energy poses great challenge to system operation. For instance, the high Rx ratio of the lines in low voltage networks makes the bus voltage sensitive to the fluctuation of renewable DG output and gives rise to the voltage volatility problem, which endangers the system security. To address this issue, researchers and engineers used to resort to the node-side flexibility, that is, the flexibility in power injections, such like the dispatchable generators and controllable loads, to follow up with the fluctuating DG outputs and compensate its impact. Nowadays, the network side flexibility, which is the flexibility in the underlying power network structure, becomes another option thanks to the advanced communication and control technologies that makes the network parameters adjustable. It will be seen later that the network flexibility has a different mechanism from node-side flexibility in addressing renewable uncertainty. By tuning the network structure, we can actually optimize the power transfer pattern and how the renewable uncertainty is coupled to bus voltages. Note that the network structure can be adjusted in either a discrete or continuous manner. And let's first talk about the discrete version, which refers to the line switching and the network reconfiguration. Let's focus on the voltage power sensitivity that determines how volatile the voltage is under renewable fluctuation. If we adopt the linear disk flow equation to describe the distribution network power flow, which is the common model, then the voltage power sensitivity can be formulated as a function of network structure as follows, where we can see that the voltage power sensitivity Rij and Xij are given by the distribution network structure with HF denoting the set of lines contained in the path from node I to the substation bus. And using this formula, we can conclude that bus I will have less volatile voltage if it locates closer to the substation, which means the sensitivity coefficient Rii and Xii is small, or the DG at bus J shares a shorter conductor with bus I from the substation. And in this case, the sensitivity coefficient Rij and Xij will be small. And therefore, we proposed the voltage volatility index of each bus given by this formula, which measures the maximum ratio of the bus voltage deviation to DG fluctuation under the infinity norm. And since this index is a function of network structure, we established the voltage volatility constraint distribution network reconfiguration, which aims to achieve both low power loss and the low risk of voltage violation under DG uncertainties by enforcing an upper bound for the voltage volatility index of each bus. And so this is the mathematical formulation of this reconfiguration problem. And you can refer to this reference for the details. And generally speaking, this reconfiguration model consists of the conventional component, for example, the objective is to minimize the power loss, and the constraint consists of some conventional constraints including the power flow equation and some physical limits, as well as the voltage volatility constraints. And before proceeding to the case study, let's first take this simple example as an illustration. The things that we assume the DG at bus J in this simple distribution network has highly fluctuating outputs. Then, for the network structure in the left figure, the fluctuating DG at bus J is much coupled to the voltage of bus I, because bus I and bus J shares a conductor from their path to the substation, and consequently the sensitivity Rij and Xij will be non-zero. In contrary, if the network is reconfigured to the one shown in the right figure, then bus I and bus J shares no conductor from their path to the substation, and consequently Rij and Xij become zero. So the voltage of bus I is much less volatile because it will not be influenced by the DG fluctuation at bus J. So now let's move on to the case study on the IEEE 69 bus system. And this figure contains a lot of voltage curves, and each curve actually corresponds to the voltage profile under a certain DG output scenario generated by Monte Carlo method. And this figure refers to the performance of the network structure given by the traditional reconfiguration model without considering voltage volatility constraints. And we can observe that the base case, denoted by the black curve, is good, but the voltage violation occurs under uncertainty because the traditional reconfiguration does not regulate the bus voltage volatility. And this figure shows the voltage curves under the same Monte Carlo samples with the network structure given by the voltage volatility constraint reconfiguration. And now we can see the performance is much better, and there is no voltage violation in all the DG scenarios. And this shows the effect of considering voltage volatility constraint in reconfiguration problem to address the impact of renewable uncertainty by means of network adjustment, discrete version. And next, let's turn to the continuous network flexibility, which refers to the smooth adjustment of network parameters. And actually, this can be done by installing novel power electronic devices to the lines, such as the power flow routers. And the power flow router is a novel kind of series controller that achieves a softer adjustment of network structure than reconfiguration. And the diagram of power flow router is shown in this figure. And generally speaking, power flow router is equivalent to adding a pair of transformers to the two terminals of a line. And the control effect of power flow router is to regulate the power transfer across this line by adjusting the equivalent admittance of this line. So in a similar way to reconfiguration, power flow router can also be utilized to address the impact of renewable uncertainty. And therefore, we proposed the chance constraint OPF in microgrids with power flow routers that co-optimizes the power flow router parameter and the generation dispatch to achieve a low operation cost and ensure sufficiently low probability of voltage violation under uncertainty. And yeah, the detailed mathematical model is omitted here due to the time limit. And please refer to the reference below for the detailed information. And in the following slides, we will focus on these 4 OPF schemes to highlight the merit of the proposed model and the mechanism of network flexibility in addressing renewable uncertainty. And the first OPF scheme is given by the normal OPF, which does not consider uncertainty and only relies on power injection flexibility. And the second scheme is given by the OPF-PFR, which considers uncertainty, which does not consider uncertainty and relies on both power injection and the network flexibility. The third scheme is given by CCOPF, which considers uncertainty and only relies on power injection flexibility. And the fourth scheme is given by the proposed CCOPF-PFR, which considers uncertainty and relies on both power injection and the network flexibility. And this figure shows the empirical probability distribution functions of the voltage of a certain bus in the IEEE 33 bus system obtained by Monte Carlo method. It compares the performances of the 4 OPF schemes under uncertainty, from which we make 2 important observations on the mechanism of power injection flexibility and network flexibility in addressing uncertainty. So by the comparison between normal OPF and the CCOPF, we conclude that power injection flexibility mainly improves the mean value of the voltage. And from the comparison between CCOPF and the CCOPF-PFR, we conclude that network flexibility mainly reduces the variance of the bus voltage. And these 2 types of flexibility resources actually take complementary effects to each other. And a coordinated control of power injection and the network parameter leads to a much better performance as shown by the red curve. Its mean value is very close to 1 per unit, and its variance is very small, which can be seen from its narrow shape. And so this implies a sufficiently low risk of voltage violation under uncertainty. And finally, let's finish the talk with a summary. So our recent works find that network provides a complementary flexibility resource to power injections to addressing the renewable uncertainty. The mechanism of network flexibility is that it tunes the voltage power sensitivity of critical bus to mitigate the renewable induced voltage volatility. And both the discrete and continuous network flexibility are promising options. So that's all for my talk. Thank you for your attention. Please feel free to contact me should you have any questions.